In this video, I would like to describe latches. I will go into the details of latches, okay, which are memory elements that are used to store bits, zeros and ones. Okay, so I will show the gate level implementation of these latches and their functionality. Okay, so let's get started. Okay, so remember that a latch is a memory element that can store a 0 or a 1. Okay, it can store a single bit. I'm going to show you here a simple latch, which is called the SR latch. It has two inputs, S and R. So S here means set and R means reset. So these are the two inputs for the SR latch. This is why it's called actually SR, because it has these two inputs. It has two outputs, Q and a Q bar. Q here means the state. That's the current state, the present state of the latch. And the Q bar is simply the complement of Q. So if a Q is equal to 0, then a Q bar should be 1. If a Q is equal to 1, then a Q bar should be 0. So these are the two outputs of the latch. Notice that the latch is implemented using two NOR gates, and these two NOR gates are cross-coupled. It means that the output of the first NOR gate is connected to the input of the second NOR gate, and the output of the second NOR gate is connected to the input. The output of the second NOR gate, which is a Q prime here, is connected to the input of the first NOR gate. So by actually doing this cross-coupling of the NOR gates, okay, we are implementing an SR latch. The SR latch has a function table. This function table is like the truth table, okay? It defines the function of the SR latch. I'm going to go into the details of the function of the latch in the next slide. Okay, so now let us go into the SR latch operation. Okay, so suppose I would like to set an SR latch. I'm going to use my highlighter here. So you can see that for the set operation, I'm going to have S is equal to 1. So that's actually is S. And R is equal to 0. Now S is connected to the NOR gate that produces a Q bar. So it's enough to have for a NOR gate, if one of its input is a 1, then the output will be 0. Now, because Q bar equal to 0, and R equal to 0. So we have both inputs to the first NOR gate are both 0 and 0, then the value of a Q will be equal to 1. So here we are forcing the value of a Q to be 1 and the value of a Q bar to be equal to 0. This is known as the set operation. Now suppose after a set, the value of S drops from 1 back to 0. The value of a Q at the Q bar will not change. The value of a Q will remain 1 and the value of a Q bar will remain 0. Now because a Q is equal to 1, the value of a Q bar is equal to 0, and because a Q bar equal to 0 and R equal to 0, the value of a Q will remain 1. In other words, we are storing the value of a Q and a Q bar. We are not changing the value of a Q and a Q bar, and the value will be stored. So as long as S and R are both 0 and 0, the value of a Q and a Q bar will remain unchanged. So this is my store operation. Now suppose I would like to reset. If I would like to reset, then the R must be equal to 1 and the S input must be equal to 0. Now because we have NOR gates, when R is equal to 1, then the output of the first NOR gate, which is a Q, will become 0. Now, because a Q equal to 0 and S is equal to 0, then a Q bar will be equal to 1. So here, because a Q equal to 0 and the Q bar is equal to 1, this is my reset operation. Now, suppose that after a reset, I drop the value of R from 1 back to 0. Okay, so now R equal to 0, S is equal to 0, the value of a Q and a Q bar will not change. They will remain unchanged. So therefore, as long as R and S are both equal to 0 and 0, the value of a Q and a Q bar will not change. Q will remain 0 and the Q bar will remain 1. Again, this is my store operation. So now R equal to 0 and S is equal to 1 can give you two possible outputs. It can give you Q is equal to 1 and the Q bar equal to 0, or it can give you Q equal to 0 and the Q bar is equal to 1, depending of course on the previous operation. Okay, so RS equal to 0, 0 is known as the store operation, and it does not change the output Q and the Q bar. Now suppose that I set and reset at the same time. So I make R equal to 1 and S is equal to 1. Now this will force Q and the Q bar to be both 0 and 0. Now here the output is undefined. Okay, so for this reason we should never actually use R and S to be 1 and 1 at the same time. Now suppose that we drop the value of R and S from 1 down to 0 simultaneously at the same moment in time. So when R drops to 0 and S drops to 0, we still have Q and the Q bar to be 0, 0. So this will force Q to change from 0 to 1 and the Q bar to change from 0 to 1 simultaneously at the same moment in time. And when both the Q and the Q bar go to 1 and 1 simultaneously, then the NOR gates will actually make them to go back to 0 and 0 simultaneously. So some oscillation will happen. So Q will go from 0 to 1, back to 0, back to 1, and so on. The same thing for the Q bar. So some oscillation will happen. So we call this a race condition, okay, in which we can have oscillation. Eventually, because there are some slight differences in the timing of the two NOR gates, one of them is going to switch to 0 and the other one is going to switch to 1. We don't know which is going to switch to 0 first and which one is going to switch to 1. So the final state will be unknown. Okay, I can actually have Q to be either 0 or 1. I really don't know what will be the final state. The same thing for a Q bar. I don't know what's the final value of a Q bar. So for this reason, we should never set and reset at the same time. So S and R should never be 1 and 1 at the same time. Now, to have a deep understanding of SR latches, let us take a look at this timing diagram. I'm going to assume that initially the value of a Q is 0 and the value of a Q bar is initially 1. So if I would like to set, I have to make S input is equal to 1 and the R input to be equal to 0. Now by making S is equal to 1, notice that S is connected to the second NOR gate. So therefore this is going to force Q bar to drop from 1 down to 0. Of course this will not really happen instantaneously, it will happen after a short delay. This delay exists in the second NOR gate. Now when a Q bar goes down to 0, it's going to force the output Q to jump to 1. Again, this will happen after a short delay depending on the delay inside the first NOR gate. So you can see that Q will go up to 1. Q bar will first change from 1 down to 0, and then after that, after a short delay, Q will jump from 0 to 1. So the final value will be 1, 0. This is my set operation. Suppose after that, we have S is equal to 0 and R is equal to 0. So the S input is going to drop to 0 and there is no change in R. So 0, 0 means that we maintain the value of a Q and the Q bar without any change. Now suppose I would like to reset. So I'm going to keep R equal to S. I'm going to keep S to be equal to 0 and I'm going to make R to make it, I'm going to have R to jump to 1. So when R goes from 0 to 1, what will happen is that the R input, when it jumps to 1, is going to force Q to become 0. Okay, so the Q output is going to drop from 1 to 0. And when the Q drops to 0 and S is equal to 0, then in this case, the Q bar is going to jump to 1. So there is actually a small delay in these two NOR gates. So first we change Q, and then after that we change Q bar. So we get 0, 1, and this is my reset state, okay? Now, if the value of R drops from 1 down to 0, so S is still 0, and R goes back to 0, so we have 0, 0, this will not change Q and Q bar. We still are in the reset state. So the value of Q and Q bar will be unchanged. At this point, this is very interesting. Notice that when the input is 0, 0, okay, for S and R, you can have two possible outputs, 1, 0 or 0, 1. This is because this is a memory element, so therefore it's going to remember the last state it was in. It's going to keep the value of a Q and a Q bar unchanged. In the case of a combinational circuit, for a given input, you will get a fixed output. In other words, the output is defined uniquely based on the input. But here, for the same input, S and R to be 0, 0, we are getting different outputs. This is because the SR latch is not a combinational circuit. It is a memory element. You can never get something like this in a combinational circuit. Finally, if I actually have the input 1 and 1, so suppose after that we set, so S becomes 1 and R equal to 0. So again, we are going to change the value of a Q and a Q bar to become 1, 0. Suppose after that we keep S is equal to 1 and we have R jumping to 1. So we have 1 and 1 at the same time. Now, when this happens, you will get both outputs of a Q and a Q bar to be 0 and 0 at the same time. Now, this is dangerous. Why? Because if the value of S and R drop simultaneously at the same moment in time, we might actually get oscillation. Okay, so the value of a Q and a Q bar will start to oscillate. I'm showing this in red. Okay, so in these red boxes, indicating that the value of a Q and a Q bar will simultaneously go to 1 and then simultaneously go back to 0 until, of course, depending on the slight differences in the timing, one of them might be 0, the other one might be 1, or vice versa. Now, when this happens, I can always reset. Okay, I can always reset by actually having S is equal to 0 and R is equal to 1. So this will force a Q to become 0 and the Q bar is equal to 1. So even though I have these red boxes indicating an unknown state, I can make it known by resetting again. And then if I would like to have set, then I can actually have S is equal to 1 and R equal to 0, and this will set it again. Okay, so this is the timing diagram, and this timing diagram describes this function table. Now, suppose I would like to build an SR latch, which is synchronized with a clock. So I need now a third input, which is called the C input or the clock input. So in addition to R and S, which are the reset and set inputs, I need a third input, which is the clock. Now, I would like to use this in a synchronous. Okay, so I would like to use it in a sequential circuit, which is synchronized with the clock. So when the clock is high, I would like to enable the operation of the SR latch. And when the clock is low, I would like to disable the operation of the SR latch. In order to do this, I need two AND gates. So these two AND gates are called enabling gates. Why? Because their output will be R and S when the clock is high, and their outputs will be 0 and 0 when the clock is 0, when the clock is low. So the output here of the first AND gate is C and R. The output of the second AND gate is C and S. So when you AND, if C is equal to 1, you get R and S, and you will have a normal operation of an SR latch. However, if the clock input is 0, you will get 0 and 0, and there is no change in the value of a Q and a Q bar. So this will give me this function table, which is shown here to the right. So if C is equal to 0, my clock is low, we don't really care about the value of S and R, and there is no change in the output Q. However, if C is equal to 1, then we have a normal operation of an SR latch. So here clock is equal to 1, SR equal to 0, 0, there is no change in a queue. 0, 1 means a reset operation, 1, 0 means a set operation, and 1, 1 means an invalid operation. So this is called a gated SR latch because we have added these two AND gates, and the clock here is used as an enable signal that will enable the operation of the enable or disable the operation of the SR latch. We can implement the SR latch differently using NAND gates. Okay, so this is a NAND implementation of the SR latch. Now here notice that my S input is called S bar. So my set input is S bar and my reset input is R bar. Okay. Now this means that they are active low. So when set equal to 0 and reset is equal to 1, that's my set operation. Okay, so when the set input is equal to 0, it means we are setting. 1, 1 means there is no change. 1, 0 means that we are resetting. Notice that here my reset input equal to 0, indicating that it's actually active low. So we reset when it is 0. 1, 1, there is no change. Finally, 0, 0 is my invalid operation. And we should not use the input 0 and 0 at the same time. This shows the operation of the S bar R bar latch. Notice that when the set input here is 0 and the reset is actually 1, so that's actually is S bar and this is R bar, that's my set operation. Notice that these are NAND gates, so remember that in the case of a NAND gate, it's sufficient to have one of its inputs to be 0 to get the output Q to be equal to 1. And when you have a Q is equal to 1 and the reset input is equal to 1, so when you take the NAND of 1 and 1, you get a 0. So that's my set operation. So Q will be equal to 1 and the Q bar will be equal to 0. Now suppose that after we do a set, then we have both S bar and R bar will be equal to 1 and 1. The value of a Q and the Q bar will be unchanged. So we are storing the value of a Q and the Q bar. There is no change in the output Q and the Q bar, so this is my store operation. If I would like to reset, I have to make my reset input to be equal to 0. So here R bar equal to 0 and S bar is equal to 1. So because here we have NAND gates, when the input R bar is equal to 0, this will force Q bar to become 1. And because here we have Q bar equal to 1 and S bar is equal to 1, we get Q equal to 0. So here we have 0, 1. This is the output of the latch. This is my reset operation. And then suppose that after a reset operation, I will have both inputs 1 and 1. This will keep my output Q and the Q bar unchanged. Okay, so when the inputs here, when the set and reset here are both 1 and 1, this means that we do not really want to change the outputs. This is my store operation. Finally, I should never set and reset at the same time. So my set and reset inputs should never be 0 and 0 at the same time. This will produce both Q and the Q bar to be 1 and 1 at the same time. If both of them drop simultaneously, I will have race conditions, I will have oscillations. So this is why we should never use S bar and R bar to be 0 and 0 at the same time. The final state will be unknown until, of course, I reset or set again. So therefore, remember that in the case of an S bar, R bar latch, S bar and R bar should never be 0 and 0 at the same time because we are using NAND gates to implement this latch. I can implement a gated SR latch using only NAND gates as shown in this slide. So this gated SR latch has a third C input where C here is the clock. So when C is equal to 0, I would like to disable the latch. If C is equal to 1, I would like to enable the latch. So notice that here the inputs are S and R. So now S and R are active high. Whereas I'm using here, rather than using AND gates, I'm using NAND gates. So when C is equal to 1, these NAND gates, these two NAND gates will act as inverters. So when C is equal to 1, the output of the first NAND gate will be S bar, and the output of the second NAND gate will be R bar. This is great because now I have again an S bar R bar latch. Now that's actually when C is equal to 1. Then we'll have a normal operation of the S bar R bar latch. We say that the latch is enabled. However, when C is equal to 0, then the output of these two NAND gates will be 1 and 1 at the same time. And 1 and 1 means that there is no change in a Q and a Q bar. So therefore, we get this function table. If C is equal to 0, then therefore S bar and R bar will be 1 and 1, and therefore there is no change in a Q and a Q bar. So therefore, we are disabling the latch. On the other hand, when C is equal to 1, we are enabling the latch. We can have 4 possible values for SR. 0, 0, it means there is no change, okay, in the output Q and the Q bar. 0, 1 means a reset operation. 1, 0 means it is a set operation, and 1, 1 means it is an invalid operation. Notice that S bar and R bar are the complement of S and R. So when I say here S is equal to 0 and R equal to 0, it means that S bar, R bar will be 1 and 1, and there is no change in the Q and the Q bar. Okay, so this shows how we can implement a gated SR latch using purely NAND gates. We have seen a problem with the SR latch is that we can have an invalid operation. Okay, we can actually have S and R to be both 1 and 1 at the same time. We said that we should never use S and R to be 1 and 1 at the same time. Now, we can design a latch that will never, okay, set and reset at the same time. This is called a D-latch. So a D-latch, rather than having 2 inputs, S and R, I will have only a single input, which is D. Now notice that this is a gated D-latch, okay, that has C here, which is the clock input. So it is implemented, okay, like an SR latch. However, we are actually connecting D to the S input, and we are using an extra inverter here, okay, this inverter to complement D. So here, if D is equal to 1, S will be equal to 1 and R equal to 0, it will be my set operation. If D equal to 0, then S is equal to 0 and R equal to 1, it will be my reset operation. The clock here is gated. It means that if the clock is equal to 0, the latch will be disabled, and therefore C equal to 0, I don't really care about the D input, and there is no change in the output Q. However, if C is equal to 1, then the output Q will depend on the input D. So Q is going to follow D. If D equal to 0, then the output Q will be equal to 0. This is my reset state. And if D is equal to 1, then my output Q equal to 1. This will be my set state. So we say that the output Q is going to follow D, and of course a Q bar will be simply the complement of a Q. It's a very simple latch, which is called a D latch, where D here stands for data. Now notice that this inverter here, okay, is necessary so that you can always make R to be the complement of S. So S here will be equal to D, and R will be just the complement of D. Now, a simple observation is that we can say that the output of when the clock is enabled, S bar here is the complement of D. So why not connect, okay, S bar here to the input of the second NAND gate? So by doing so, I can actually eliminate, okay, this inverter. So this will be a clever implementation of the D latch. It will have exactly the same function table. So, but I eliminated the need for the inverter. So the inverter here is using this NAND gate. So I'm using this NAND gate as an inverter when C is equal to 1. So when this C is equal to 1, the latch will be enabled. This NAND gate will act as an inverter. So here the R input, okay, this is my R input here, is simply equal to S bar, and S bar will be equal to D bar. So therefore we have achieved, okay, we have inverted the D input by taking the output of this first NAND gate. So this first NAND gate is used as an inverter when C is equal to 1. And therefore, there is no need for this inverter, and this will be a simpler implementation for the D latch. To have a good understanding of the D latch, we really have to look at the timing diagram. Okay, so this is a D latch that has a clock input. So this actually is my clock enable. So that's my D input here. And this is my clock input, my C input. Now, notice that the clock here is just a periodic signal. We already have seen the clock before in a previous slide. So when the clock is 0, the latch is disabled. When the clock is 1, then the latch is enabled. The D input here is selected to be just a random signal, okay, that goes actually from 0 to 1 back to 0 randomly. The S bar and the R bar, these are the outputs of the first two NAND gates. Okay, so I'm going to show first S bar and R bar, and then I'll talk about the Q. Or we can jump even from D to Q, even without even going into the S bar and R bar. Now notice that when the C input is low, is 0, right? When C is equal to 0, S bar and R bar will be both 1 and 1 because we are using NAND gates. Again here, okay, when you can see when C is equal to 0, S bar and R bar are always equal to 1 and 1. Same thing here, and so on. S bar and R bar are equal to 1 and 1. Now, when C is equal to 1, this is where we are enabling, okay, we are enabling the latch. Notice that S bar here is just the complement of D. So this first NAND gate here, which is shown, is acting as an inverter. So this is D, okay, that's actually how D is changing, okay, when C is equal to 1. Notice that S bar is just the complement. Okay, it is just the complement of D, and R bar is identical to D. Okay, because R bar actually is, we are complementing S bar, and therefore we get exactly equal to D. Okay, so you can see that R bar is identical to D, whereas S bar is just the complement of D. This is when C is equal to 1. Same thing here. When C is equal to 1, you can see that S bar is just the complement of D. Okay, when D is equal to 1, S bar will be equal to 0, and when D is equal to 0, S bar will be equal to 1. Notice that R bar is just following, okay, D. Notice that the Q and, I'm showing Q here, Q bar is just the complement of a Q. Now suppose I don't really know initially what's the initial state. I'm showing that Q is initially here in red, indicating that I don't know what's the initial state. Okay, so the initial state could be 0 or 1. We don't really care. So once we have C is equal to 1, okay, it means that the latch is enabled. Okay, so we can look at D and we can simply copy D. So therefore, the value of a Q will be identical to D. Now notice that if we look at S bar and R bar, when S bar equal to 0 and R bar equal to 1, it means a set operation. When S bar is equal to 1 and R bar equal to 0, it will be a reset operation. In other words, Q is just copying R bar, and R bar is nothing by D. So in other words, okay, Q is just following D when C is equal to 1. Notice that here, okay, when C is equal to 1 here, notice that how Q is just following D. It is identical to D. Now I ignore the delay. Usually this Q output will be delayed. It will be shifted to the right by a small delay according to the delay inside these NAND gates. So these gates have delays, and the output Q, also S bar and R bar, all of these will be delayed. But I'm ignoring the delay. I'm just showing here ideal gates as if there is actually 0 delay in these gates. Notice that here, okay, when C is equal to 1, notice that how Q is identical, okay? Q is identical to D, okay? It's identical to D. On the other hand, when C is equal to 0, there is no change in the output Q. So Q will be just the same value as the previous value of a Q, and there is no change in a Q. So as long as, okay, the C is equal to 0, there is no change in a Q. Okay, so Q will be just remain the same value as long as C is equal to 0. So once C changes to 1, then therefore there will be the value of a Q will be identical to the value of D. Okay, that's the D latch. This is how we can look at the timing of the D latch, and this is how we understand the function table of the D latch. We can look at the graphic symbols of latches. Okay, so this is actually the graphic symbol for an SR latch. It has, okay, in addition to S and R, there is actually a C input. So it has 3 inputs in total. It has 2 outputs, Q and Q bar. Notice the bubble here, or the small circle at the output. It indicates that the output is inverted. So we get 2 outputs. We get a Q and we get a Q bar. In the case of an S bar R bar latch, notice that here the inputs are inverted. So notice that these 2 bubbles or small circles indicate that the inputs are inverted. It means that it is active low. So we set here when the input is 0, okay, and we reset when the R bar equal to 0. Okay, that's when we reset. This is the symbol for a D latch. Okay, notice that it only has a D input. D means data. Okay, and there is the clock here, which is used to enable the latch. Okay, that's my clock input. It does not really matter how we implement these latches. Okay, eventually all of these latches are implemented with transistors using modern CMOS technology. So what we have seen is just logic diagrams that explain the functionality of these latches. But in reality, they are implemented using, at the lowest level, they are implemented using transistors in modern CMOS technology. Now, I would like to mention a problem with latches. I would like to conclude with this slide, okay, about latches and why latches are not really the proper memory element for synchronous sequential circuits. What we have seen in the previous slide is that the latch is sensitive to the level of the clock. So as long as the clock is high, then the output Q is equal to the input D. That's a D latch, okay? So as long as the clock is high, the latch will be enabled, and the Q is simply equal to D. Now suppose that we take here the output Q prime. I take here the Q prime and connect it back to the D input. Now you might actually ask a question, why are you doing something like this? Why do you take the output Q prime and you connect it back to the D input? Now this will be useful, for example, for building a counter, okay? If, for example, if a Q is equal to 0, you would like to actually change it to 1 in the next cycle and so on. If it is 1, you would like to change it to 0. So in some circuits, it is useful to take the output, okay, for example, of a latch and connect it back to its input. So suppose that we do this, okay, in the case of a latch. Now the problem is here for the latch is that as long as C is equal to 1, the clock is equal to 1. So as long as the clock is high, the latch will be enabled. And this means that if a Q is equal to 0, Q bar will be equal to 1. So we're connecting here, D becomes 1, and therefore the Q is going to follow D, so Q is going to jump from 0 to 1. So when Q jumps from 0 to 1, Q bar is going to drop to 0. And because we are connecting it back to D, then in this case, Q is going to follow D, then actually Q is going to drop back down to 0. So therefore, Q is going to oscillate. It's going to go from 0, 1, 0, 1, okay, as long as the latch is enabled, as long as the clock is 1. And this is not good. This is not good. So the designer might actually want to change the value of a Q once. He wants it to change it once. If a Q was 0, he wants to make it 1, or vice versa. But he does not really want actually this to oscillate. So the latch, the problem with the latch, okay, is that as long as the clock is high, the latch is enabled. And therefore the output Q is, okay, so it's going to follow the D input. And because of this, we have this kind of oscillation. The final value of a Q, so once this clock drops down to 0, we don't know what's the final value of a Q. The final value of a Q can be either 1 or 0. It's unknown. That also gives uncertainty, okay, in the output queue. So for this reason, people don't use latches, okay, in synchronous sequential circuits. They use a different memory element, which is the flip-flop. The flip-flop actually solves the problem of a latch. I'm going to describe flip-flops in my next video. So this is the end of this video. In my next video, I'll talk about flip-flops. I'll talk about characteristic tables and equations. Thank you for watching.